Okay, guys, this is a follow-up of the problem that we just finished. Um, just for you to remind you, is we have a steam power plant that operates on an ideal reheat Rankine cycle. We have a low pressure and high pressure limits. We know that it's 12 kilograms per second, and we have a superheated temperature of 500 degrees. We are giving uh, two conditions, two restrictions. So the moisture content should not exceed 10%, and we are asked to get the reheat cycle, the reheat pressure, as we discover in the solution, the manual solution, we need to iterate. So this will be better solved by is, which is this tutorial. We're going to start by starting is. And I like to and 37. One nice thing that we can do is we can open a diagram window. Sorry, we didn't close the comments here. And in this diagram, we can just think that this is a good size. And we can use it just to help us. Here we have the solution that we just did, so maybe we don't need it. So we're gonna start by stating our states, and good practice is to just saying what we are doing. So pressure 1 is 10 kilopascal, and we know that quality 1 is 0. It's an ideal gas. With that in mind, we're gonna use steam. In this case, we're going to use this formulation steam. So we have our enthalpy. Sorry, we need to say H1 impulse, and we're going to compute volume 1 as the volume. It's a way to get the pump work. So state 2 is a pump outlet. We said that the work of the pump is equal to P1 times the pressure difference. We have to state pressure 2 to be 15 megapascal, which is 15,000 kilopascal, and then H2 will be equal to H1 plus the work of the pump. We can press F2 or solve just in case we are in doubt. First, we check that our unit system is consistent with our solution. We said it's okay. Oh, I remember why we would use this one. So we just take steam out. This is a more accurate formulation. So we said we have a problem of number of units, and we notice here that we are not giving T1, so we need to change temperature for quality. We have it. And then we continue. This is boiler outlet or turbine inlet. And a way of doing this a little bit faster could be copying, Ctrl C, Ctrl V, then start here. And I will press F11, which I will say change 1 and replace with 3. Replace all from the cursor position to the end. I did some things that I didn't want, but I am changing them anyway. So this is P2, T3 equals 500. You can check it here, 500. And I'll change this to say T3. And instead of volume, I will compute the entropy. So we could just press F2 to check that we don't have any problem, and we cannot go to stage 4 because we don't know it. Stage 5 because we don't know the pressure, but that was a problem of the when we were doing by hand. We can state 4 and it will be extraction pressure, reheat inlet. So we don't know what the pressure is, but we know this enthalpy will be equal to S equal to S4 and P equal to P4, which we don't know. S3 equals S4. That's everything that we know. Go to state 5. So pressure turbine inlet, and we can put the same here, high pressure. If we try to solve it at this point of time, we cannot solve it because we are missing P4 to check and say that we are missing one variable and P4 is among them, so we are okay. P4 is equal to P5 and T5 it's equal to 500. We're gonna copy this and change F11, change 3 to 5. check, we have everything. Still same problem, we're missing one set of data. We press F2, we're still missing P4. So now we arrive to the state 6. Condenser inlet. We know pressure 6 equals pressure 1. We don't know the outlet, but we know two things. S X6 is 90%, and it said that we should not exceed, but we know that the lower the pressure, the higher the lower the quality, and we would like to expand as much as we can, so we're going to use that 90% as we explained in the problem. We also know that S6 equals S5, and that's everything that we should know, because now we can copy these two and say that enthalpy 6. Let's say first with entropy. Entropy 6. Actually, you can save 1. Hold on. We know this number for sure, so this is x equals x6 and p equals p6. We know that the same is for the entropy. We copy this. You see, what we are doing here is exactly what we did in the problem. We're computing this enthalpy, we're making this equal, and then the problem will go backwards to get which pressure 5 makes this statement true. So we press F2. Oh, this error in this. Let's do it again. There's a syntax error in this equation. Okay, let's look for it. We have two commas here. F2. And we can see that the pressure that we have is 2000 and we can see that our pressure is 2141 kilopascal, which is 2.14. It's very close to 2.34 that we have in our solution. This will be a bit more exact since we are we're computing the exact properties at each iteration, opposite to the interpolation that we did in our solution. Thank you guys. In our next video we are gonna explore more options using is, building on this program that we just did. Thank you.